Okay, good day. This is AP Calculus. I'm Mr. McCully. This is the section on 3.9 differentials. We are skipping 3.8, so let's get right to it. Our learning goal for today is to understand the concept of a tangent line approximation, and we are going to compare. Let's see, I don't want that. Okay, here we go. And we're going to compare the value of the differential dy with the actual change in y, and that actual change in y we're going to call delta y, or the change in y. We're going to estimate propagated error using differentials, and we're going to find the differential of a function using differentiation formulas and equations that we've already used. It's kind of a review. So what is the derivative as a differential? Well, you've seen this notation. And I suppose I should take a step back and say the reason that we're talking about this section is the arrangement and use of differentials becomes very important when we move into the next chapter on integration. All right, so we need to understand what a differential is, and we also need to understand how it's manipulated. All right, so when you see something that looks like this, we've done this kind of notation already. And when we say that we say take the derivative with respect to x of y equals some function x. And we know that that thing is, you need to use a pen there, Macaulay. Okay, there we go. Dy over dx is equal to f prime of x. Now, here's the thing. This is the differential of y, and that thing is the differential of x, and it represents that derivative. But it is also still a fraction that is the ratio of the differential of y to the differential of x. And just like any other fraction, if I multiply both sides by dx, I can, or consider dx to be a variable and then multiply both sides by dx, I can say that dy is equal to f prime of x dx. And this is my differential notation. And it's what we're going to use when we get into chapter 4. And that's what we're going to be using right now. So just to kind of formally define these things, the differential of x is dx, and the differential of y is dy. And from the last one, we have this. And what we're going to get to is we're going to say that the actual change in y is approximated by dy. And since dy is going to be approximately equal to the change in y, we can replace this dy with the actual change in y and say that the actual change in y can be approximated by this differential statement right here. Now, what does that mean visually? Well, I've got a visual approximation here. So let's just say, as a for instance, we have a function that looks like an exponential function. It may not be, but let's say if it looks like it. So what we're going to do here is we're going to talk about an actual change in x, and we are going to say that the change in x is actually equal to the differential of x. Now we have a point here, and we have a point here that's going to be right above it. And so the distance to y for both of these, this is our actual change in y. That's our actual change, not in x, Macaulay. That is our actual change in y. Now, if I do a tangent line, and that's why I have this right here, although I'm probably going to have to move it just a little bit because that's a secant line. All right, let's see. Let's see if we can get this to look right. I need to go just a little bit more. All right, let's pull this down. There we go. All right, so this is my tangent line approximation. So if you think about it, if I were to plug in this change in x value, or x plus change in x, if this is x, this would be x plus change in x. Well, these two distances are approximately the same distance. It's approximately the same. Now you can see this is the error. This is the difference between what our approximation is and what the actual value is. So if I were to follow this along, this value here becomes my actual dy. So back to here, the actual change in y is approximately equal to what dy is. So you can see that we have a little bit of error. And we can say the bigger that dx is, the bigger our possible error is going to be. The smaller that the change in x is, the better our approximation is. If it's only this far, we're almost right on it. So again, this is just an approximation. It's not an exact thing. Okay, so calculating propagated error with differentials, the possible propagated error is just dy. And again, this is approximation. The relative error is dy over the actual value of y, and I will show you what that means in one of our examples. But what you can kind of think of this as percent change. And if you remember way back, probably 5th or 6th grade, you did percent change. And the way you did that was you took the new value and you subtracted the old value and you divided that all by the old value. And if it was positive, you'd say that that was a percent increase. If it was negative, you'd say it was a percent decrease because the new value was smaller than the old value. You can kind of think of that the same thing. This is the actual value for y calculated at the original place, and then this is your differential calculation of y, which this would be the exact dy. We would consider this to be exactly dy, where this is our approximation using differentials. So that's where we're at, and the examples are they're not too bad. I am going to start on page, let's see here, 240 out of the book. If you've got that with you, start with a first one. And this is one where we're at least the goal, find differential of a function used in differentiation formulas. That's what this one's going to be. And so number 16 gives us this equation. They say y is equal to the square root of x, and then it's plus 1 over the square root of x. All right, so it says find the differential of y of the given function. So I am supposed to find dy. Okay, well, let's try that. Let's do the derivative with respect to x. Okay, find dy. So this thing here, let's rewrite before we actually do any differentials, and let's rewrite this as y equal to x to the 1/2 plus x to the negative 1/2. I think that shouldn't be too much of a stretch. Then dy over dx is going to be, let's see here, we'll have a half here, x, I subtract 1 from a half, I get negative 1/2 plus, and then I bring down the half for this one, so it'll be negative a half, and then times x, I subtract a half from negative, or excuse me, I subtract 1 from negative a half, that'll give me negative 3 over 2. And that thing's going to reduce down to, so I'll get 1 over 2, and let's not use square root. Let's make it 1 over 2x to the 1/2 plus, and since it's a negative, we'll make that a minus. I got ahead of myself, and I hate it when that happens, because I got to rewrite everything. So I got 1 over 2x to the 1/2, and then minus 1 over 2x to the 3/2. Now, if I want to make this into a single fraction, I have to multiply the first one by the funky 1, x to the, or actually be x to the 2/2 over x to the 2/2, so that I get 3/2 there. And so for both of them, I'll have 2x to the 3/2. And then when I multiply by x to the 2/2 over x to the 2/2, well, x to the 2/2 is just 1, so I'll have x in the first fraction, I'll have minus 1 in the second fraction. Now, in the back of the book, changes this back to a radical and reduces it. This is good enough. I think we'll leave it like that. And we'll say that this is dy over dx. Now, that's not what they want. They want us to find dy. So all we have to do to this is multiply both sides considering the differential of x as a variable and say that its dy is equal to x minus 1 over 2x to the 3 halves and then times dx. That's it. We're done with that one. Not too bad. Okay, next example, number 28. Number 28 is a word problem. I suggest that you check it out, but I'm just going to read it. It says the measurements of the base and the altitude of a triangle are found to be 36 and 50 centimeters respectively. The possible error in each measurement is 0.25 centimeters. Use differentials to approximate the propagated error in computing the area of the triangle. Now first, we know that the area of a triangle is a half base times height, and we know that when they're creating this triangle, whatever it is, they say that they want the base to be equal to 36 centimeters and the height to be equal to 50 centimeters, but their measuring device, whatever that might be, in each one, dB and dH could be the same, they could be off by the same amount, plus or minus 0.25 centimeters. So they want us to approximate the change, the possible change in error, regardless of how big of an error they made in measurement. So that's what we're looking for. So we're going to use a differential approximation, dA, to calculate this thing. Now, this is a product, so when I derive this thing, I can't derive it with respect to necessarily any variable. We're just going to do it as marginals or differentials. And I'm going to say that dA, I still have to consider this to be a product of some sort. So it'll be a half. I'm going to put that out and start trying to get you in the habit of putting those constants out in front. And so the derivative of the first would be dB. So it'll be dB times h. I'll rewrite it as h dB plus I'll leave the first one alone. The derivative of the second would be b dH. And that would be our differential for that thing. And again, we're just using the product rule. So fairly straightforward. That's pretty good. So my approximate change in the area. Well, let's see here. I have my half out front. I know that my actual H is 50, and the possible change in length, and again, this is error in measurement, could be as small as minus 0.25 and as big as 0.25. And so plus or minus 0.25 plus, and then I'll go H was 50, so B is 36. And again, the possible change in height could be plus or minus 0.25. And so when I multiply that all out, I get a value for dA, and we're saying that that's approximately equal to our change in A. All right, you multiply all this out, I get, let's see here, plus or minus 10.75 centimeters squared. So if you know that your error in measurement is only 1/4 of a centimeter off for both your base and your height, you could be off by have a full 20 centimeter square change in area. It could be anywhere from a plus point or 10.75, almost 11 centimeters to the good, or almost 11 centimeters to the bad, depending on your measurement. All right, last one, doing well, keeping this short. My last one is page 34, and again, it's another application problem that you should probably read through. It says the total stopping distance t of a vehicle is given as t equals, let's see here, 2.5x plus 0.5x squared, where t is the distance to stop in feet, and x is, let's see here, miles per is the speed in mph. All right. So remember, even though this is speed in mph and t is measured in feet, they've modeled this function so that that is not a problem in our units change, and that they're telling us that there. So they say use approximate the change and the percent change in total stopping distance as speed changes from x equals 25 to 26. Actually, let's make it, I gotta do the whole thing. All right. X equals 25 to x equal to 26. Now, what that says is that the change in x is going to be equal to 1, and that's also going to be our dx. So when I do this differential derivative with respect to x, I get dt over dx is going to equal 2.5 plus x, and that's just doing that, do the derivative. Now dt, the change in t, which is what we're trying to find, and approximate the change in time. That'll get, let's see here, it'll be 2.5 plus x times dx. Well, we know these things. I know that my original, this is my original speed, is going to be 2.5 plus, let's see here, x is, I don't want all that, I don't need as many parentheses there, 2.5 plus 25 times, well, dx is just 1, so the approximate change in stopping distance is approximately equal to that dt, and that's going to be 2.5 plus 25, which would be 27.5 feet. This is they wanted the approximate change. I don't need all of that. Jeez. So if you had went from 25 miles per hour to 26 miles per hour and decided to stop, it would take you approximately 27.5 more feet. Now, how is that in terms of a percent change? Well, the percent change is, again, it would be dt over t, which we got from, let's see, where is that? Right here. Would be our relative error change. Now, we've already calculated dt. We know what that is. It's 27.5 feet. What is t? Well, I've got an equation for t, and remember, I kind of went back to that old school percent change. Old new value divided by or minus old value all over old value. So what we're going to do is we are going to calculate t as if we're using this original amount. So t is going to equal that 2.5 times 25 plus 0.5 times 25 squared. Now I've already calculated that, and it comes out to be 375. And again, it'll be feet. So if you're going 25 miles an hour, it takes you 375 feet. So what does that mean in terms of the percent change? Well, 375 feet ends up turning out to be, this is 0.0733 repeating, I didn't write it any further, which is 7.33%. That is the percent change, the approximate percent change of stopping distance when you change from 25 feet to 26 feet. Now that's going to be different if you stop from 26 feet to 27 feet. All right, because again, stopping distance is a quadratic function, so it's always changing. Well, that's all I got. That's much shorter than the last section, just under 20 minutes. So to the Star Wars fun fact of the day. The movie Star Wars Rogue One, the first anthology movie has the character Saw Gerrera, played by Forrest Whitaker. That's that older guy. And that character is um, the first character to come from the Clone Wars TV show and moved over into, so most characters so far have been came in the movies and then they've used them again in TV shows, a lot of the animation. And Saw Gerrera is a new one, but he isn't the first character that was first seen in a TV show that moved into the movies. Can you guess what the first character was? Well, if you guessed Boba Fett, let's see if I can get there. Boba Fett, he was first shown in Star Wars The Holiday Special. I've used the Holiday Special before, and Boba Fett showed up as an animated character at the beginning of Star Wars Holiday Special. They had an animated introduction, something that they couldn't do with a TV budget that you could do, and they showed him as a bounty hunter on a different planet. Well, that's all I got today, guys. I hope this one was a little bit better than the last one. Have a good day, and I will see you in class. Goodbye.